Hey guys, welcome to the video 6-2C, sequences as functions. So today we're going to continue looking at sequences, but we're going to be using a different notation and see how that changes things. So as our do now, I'm asking you to find an explicit formula for the following sequence: 10, 15, 20, 25, 30, 35. So hopefully you can recognize that these are going up by adding 5, right? 10 plus 5, 15 plus 5, 20 plus 5, etc. So this is going to be an arithmetic sequence with a common difference of 5. So using the formulas we've been talking about, that means we're going to be using a sub n is equal to a1 plus n minus 1 times d. Plugging in our values, we get 10 plus n minus 1 with a d value of 5. Now, typically when we have our arithmetic sequences, we want to expand out this parenthesis so it is in our simplest form. So I'm going to distribute this 5, and I get, and in its simplest form, I get a sub n is equal to 5n minus 5, okay? So we should be fairly comfortable doing that. So now my question to you is, can you graph this sequence? And I'm just going to change that to an n because that's what we're using here. But how would we graph this? Well, basically, if you were to graph a sequence, your x-axis or your n values are going to represent the bottom axis. Now, those are your term values. So what kind of numbers are our terms? Well, we have the first term, second term, third term, right? It's going to be all of these numbers going up by 1, increasing. So 1, 2, 3, 4, 5. Now, I think we only have 5 values. We know that this continues on, so we could graph more if we wanted to. But I'm only going to be concerned with this graph for the first couple. Okay, now remember, we can always choose a different scale for my x and my y. So to fit the numbers up to 35, I'm actually going to go by 5. So 5, 10, 15, 20, 25, 30, 35, 40, 45. Now notice I have this axis labeled with an AN, right? That is the value of my term at that particular place mark. So for the first term, a sub 1, we have 10, right? Because a sub 1 is equal to 10. The first term is equal to 10. A sub 2, right, is equal to 15. A sub 3 is equal to 20. A sub 4 is equal to 25. How far did we go up here? Okay. A sub 5 is equal to 30. We did 6. Yep. And a sub 6 is equal to 35. So we would graph this in this way. Now, do we connect the points? And the answer is no, because there is no 1.5 term. There is no 2.5 terms. Each one of these are discrete values, okay? So we would leave this in this way. We could continue going up with the pattern if we wanted to, but we're really just going to be focusing on this. So now looking at this graph, what does it look like, right? And hopefully you're saying that it looks linear, right? And you're correct. If we look at the equation, right, other than the a sub n, that looks exactly like a slope-intercept form of an equation. So it is going, these arithmetic sequences are going to take linear formats when we do graph them. So now the question is this a relation? Is this relation a function? Now remember, something is a function if for every input there is exactly one output, or it passes the vertical line test. So if we were to take a vertical line throughout this entire graph, we would see that, yes, this relation is a function, okay? So now if it's a function, we should be able to identify what the domain is and what the range is. So are there any restrictions on my domain? And the answer is yes. As I said before, there's no 1.5 term. There's no 2 3/4. There are no decimals and fractions in our domain. So we're going to say that our domain are the positive integers, because there are no, 0 is not included, right? There is no 0 term, and negatives are not included. There is no negative first term. So our domain is positive integers. So how does that affect my range? Well, when we consider our range, those are our values on our y-axis. Well, these are also positive. They are also integers. And we even have a starting point, right? If I don't go below 1, my starting y value is going to be 10. So my range here is going to be positive integers greater than 10. Okay, so that's the type of values that are included in my range. So now the question is, we've set it's a function, we identified the domain and range. Can we write this in function notation? And the answer is yes. How do we create something of this nature? Well, remember, function notation typically uses f of x, right? Well, in this case, we're looking at f of n. So how do I write this? Well, f of n means I'm going to be plugging n into my formula. So what am I plugging? 1, 2, 3, 4. The explicit formula allows me to do that. So if I wanted to write this explicit formula in function notation, I would write the exact, I think I made a mistake. Sorry. The exact same explicit formula, just replacing the a sub n with an f of n. Okay, so what do we take from this? Well, anytime we see a sub n, we are going to rewrite it. We are going to understand that it is the same as f sub n. So when you see multiple choice questions, they might put it in this format. Those would be the same. Okay, so what would a sub n plus 1 be? Well, I would have f of n plus 1. What would a of n minus 1 be? F of n minus 1. So again, it's just showing that we can plug our place setting into this function notation to continue. Okay, so explicit formula. In subscript notation, which is what we've been working with, we would write a sub n is equal to 5n plus 5. In function notation, again, we are just switching this. So what else changes in the equation that we look at? Well, if that is written in function notation, so does my initial term, right? Typically, we would write a sub 1. Well, if we're writing it in function notation, that is f of 1. Okay, so f of 1 is going to represent my first term. Everything else is the same. Now, you notice they put the common difference multiplying in front of the parentheses. That's the same. Remember, commutative property says we could switch that in either order. So this end of our equation is actually the same. So the only differences that we have here are the f of n and f of 1. So let's look at another example. Find an explicit formula for the following sequence. Now, I did make a typo here. There should not be 2 12s. Okay? So we're going from 3 to 6 to 12 to 48 to 96. Well, how do we do that? 3 times 2 gives me 6. 6 times 2 gives me 12. This should have been a 24. 12 times 2 gives me 24. 24 times 2 gives me 48. And 48 times 2 gives me 96. So this is going to be a geometric sequence with a common ratio of 2. Okay, so now in subscript notation, typically we would write a sub n is equal to a1 times r to the n minus 1. So that's an is equal to, what is my first term here? 3 times my common ratio of 2 to the n minus 1. Can we write this in function notation? The answer is yes, right? Remember, we're just replacing any a sub n's with function notation. So if I wanted to rewrite that formula, right? f of n is going to be equal to my first term, which we said was f of 1 times r to the n minus 1. And if I wanted to write it specifically for this problem, f of n is going to be equal to 3 times 2 to the n minus 1, right? Almost exactly the same. Okay, so we should be able to go back and forth with these two things. So now let's graph this sequence. So we want to, again, my x, which should really be my n values, are going to be my place settings, right? My first term, my second term, my third term, my fourth term, my fifth term, and my sixth term. The a sub n, or also f sub n, I keep getting those two confused, a sub n, f of n. Okay, so it's a sub n, f of n. Okay, so that's how you would read those two. Those are interchangeable. So we want to have up to 96, so I'm actually going to go by tens on this axis. Notice for this one, geometric, it moves a lot quicker. 50, 60, 70, 80, 90, and 100. So let's plot those points. So my first term, right, is 3. So where I have a 1, I plot 3. My second term, 6, slightly higher than that. My third term, 12. My fourth term is 24. My fifth term is 48. And my sixth term is 96. Okay, so now looking at this graph, what does it kind of look like? Well, hopefully you can tell that this looks like an exponential function, right? And that should make sense because we have a base raised to an exponent that changes, right? The exponent has my variable. We also see that in this graph, right? We start really, really low, and then it increases really, really quickly, which would be exponential growth in this case, okay? So is this relation a function? Well, it mimics an exponential function, so yes, it is, okay? We even wrote it in function notation because we knew already that this was a function. What is my domain? Well, this function has the same restrictions as the last one. We can only plug in the numbers 1, 2, 3, 4, and bigger, which are my positive integers. Okay, now for the range in this case is going to be the same, but you have to be careful, especially with common ratios that are fractions. You might have more decimals and fractions when it comes down to geometric sequences. Also, if my common ratio is negative, you might also get flip-flopping between positives and negatives. So you don't want to get into the habit of just assuming everything is a positive integer. So for the range, you definitely want to always evaluate the values that you have. But in this case, we do only have positive integers. And they are all greater than my initial term, which is 3. Okay, so that's how the graphs connect to our sequences. Again, we can't connect the points because there is no 1.5 term, so we would have to leave it in this way. So we've already talked about these two things. Again, I already wrote this before. F of n is equal to f of 1 times r to the n minus 1. Both of the examples we did today are representing explicit formulas as functions. Please note that this is still true for recursive formulas. So if we go back to the original, okay, let's go back to the original. If we're looking at this, could we write this as a recursive? In function notation? Well, in subscript notation, right, we always have our initial term of a sub 1 is equal to 10. In function notation, this becomes f of 1 is equal to 10. In subscript notation, we would typically write a sub n is equal to a sub n minus 1 plus 5, the common difference. So how would we write this in function notation? Well, we take anything with a and a subscript and turn that into a function notation. So if it's a sub n, it would be f of n. If it's a sub n minus 1, it would be f of n minus 1 plus 5. Okay, so recursive formulas can be rewritten in function notation. So just take 1 second, or a minute or two, and write a recursive formula in function notation for this geometric sequence. Okay, what parts do we need? Well, recursive and function notation. Right, a recursive formula in function notation. We need our initial term, which is going to be f of 1 is equal to 3. And my f of n term is equal to 2 times the term before it, which is f of n minus 1. Okay,